Oh, wow. That's cool. Analyze the moments, 'cause there's a few different distances.
Okay, so this one here, we've got this is the only one due tomorrow. So there you go. So what we got there is we've got a motor that's lifting up this platform. We've also got a hydraulic cylinder there that's pushing on it too. And we're just pushing that up slowly. So as long as you're pushing it up slowly and it's not accelerating, you could use statics to analyze this. So what you want to do here is find the reactions at pin joint A and in the hydraulic cylinder. So that's what you want to be doing on this one. Okay, so what you do on this is what you do on all of them. You turn it into a free body diagram, okay? So whenever I see those distributed loads, I want to get those resolved into a point load. So I'd get a force right there in the middle, right? And see, that middle is 1.5 from that point, this edge right here. So it's 2.5 meters from A. And what, 900 by 3 ought to be 2,700, I think. So get those distributed loads turned into point loads. And then you've got this hydraulic cylinder. Well, that acts just like a link, okay? Because it's got a pin on either end and no loads in between. So that's going to be just a link. And then you got a pin joint. Okay? So you're going to have REX and REY. So this is always step number one, is get these things kind of turned into free body diagrams. All right, and we got everything dimensioned. Probably going to take a moment. Do what now? What are we going to do on this one to start? Yeah, write down the 3 equations, which are sum of fx, sum of fy, and sum of moments. Which equation do you think you'd start with? Yeah, about where? Probably A, yeah. Okay. So I keep repeating this for a reason. I just want you to kind of get it hardwired so you kind of know how to approach these things. Okay. So, off you go. So, you've got your free body diagram. You can take moments about A, and, you just go ahead and do that. All right. So sum of MA, you'll have that couple, 200 Newton meters positive. You're going to have the 600 newtons for the platform by 2 meters, right? Negative because it's clockwise. So 4-meter platform, so that 600 newtons is in the middle. And let's see, I've been changing this around for a while. You do have to include the weight of the platform, right? It's given us 600 newtons. Okay, yeah. Okay, great. All right, and then you're going to have the 2,700 times 2.5 negative, and then plus, because it's counterclockwise, 3 meters, which is 1 and 2. That gets you 3, and then you're going to have this, but all you really want is the y component. So that'll be sine 72 RC. And that'll get you RC and then some of FY and some of FX to finish up. Right. So that's how you do this. So the methods are pretty similar to any other problem. You get a good free body diagram with dimensions. Before you create the free body diagram, it's a real good idea to know where you're going to take moments about, because you want to dimension from that point to all the forces. That way you can do the moments pretty readily. Okay?
If you had taken the moment at C, it still would have worked, right?
Yeah, you could take the moment about C because REX goes through C also. So REX and RC both cancel. They create 0 moment about C. So then if you take the moment about C, you can solve for REY. Yeah, no problem. Okay.
So is that distributed force separate from the weight?
Yes.
Okay.
Yeah.
I was confused about that.
Oh, okay. Yeah, they're 2 different things. There's the weight of the platform and the distributed force. All right. So, question?
Where did the 2,700 newtons come from again?
The 2,700 newtons is the distributed load from B to D. which is 900 newtons per meter. So times 3 is 2,700. And it goes in the middle of the load, not in the middle of the platform, but in the middle of the load, which puts it 2.5 meters from A. Okay. All right. So we're doing all right with that? Questions on that? So, there's kind of a common theme here. Some of these pictures you start off with can get kind of complicated, especially if you look in textbooks and things, they got whatever. I've seen wheelbarrows and machines and airplanes and all sorts of things they have you do statics equations on. And you just want to boil it down to just a simple force diagram. And usually you start with a moment equation. That seems to be the norm, and figure out where that's going to be about, get 2 of the unknowns eliminated for the point you take the moments about, and then dimension from there to all the other forces, okay? And then you can come up with a moment equation. Okay? And then very likely you'll do 2 force equations after that because they're easier, okay? All right. Now there's exceptions, of course, but that's the general approach on these things. So it's really important to get a good free body diagram. If you get that, everything just kind of falls out. If you kind of understand the basic approach and get yourself a good force diagram drawn up that's dimensioned and ready to go, you're good then. You can just do a moment and then do force equations. That's about it, okay? Okay, so we good on that? Questions? All right. All right, now let's have a look. We've been kind of going into these 2-dimensional problems now, because a lot of what we do here is 2D equilibrium. When you're working, you often deal with that. So let's take this little bracket here. It's just a little bit more complicated than the other one. And let's find the reactions on this. Anybody tell me what page we're on with this one? 430. 430? So yeah, we're on 430 is where we're at. So page 430. All right, and so, just like you do, you come up with forces on that and create a free body diagram. So I see that pin joint at A. So I don't really think about it too much. I just put 2 forces on the pin joint, REX, REY. It's just that simple. Don't make it more complicated. And then I see our roller at C, and so I put a force perpendicular to the flat surface. And the general rule there is if you take 90 minus the ramp angle, you get the force angle. Okay, so I just go ahead and I do those things, and that gets me a free body diagram. I also have to remember that force there, the 48 newtons, okay? So there you go, all right? And again, get kind of tunnel vision when you make these free body diagrams. Don't think too much. Pin joint, 2 reactions, roller, 1 reaction perpendicular to the surface. That's about it. Okay, so now what we want to do is we want to find the reactions. And I see that pin joint up there with 2 forces on it, of course, REX, REY. And so I'm going to take moments about that, okay? That's how I'm going to approach this. So what I want to do is I want to get dimensions from that point A to all of the forces that I've got to deal with, okay? So that's the next thing that I want to accomplish here. So I'm going to, there's a dimension right there, straight down from A to that 48 Newton force at B. But now another thing that I want to do is I want to get that angled armature, that 8 centimeter armature, and I want to get that so that I can, oh, you're not locking up, are you now? Come on, it's just silly. All right, let's see if I can shut that thing down and start it up again. So what I want to do there is I want to get dimensions, as I was just saying there, from, it looks like I lost some stuff here. Get dimensions from A to B, which is pretty straight up because the bracket goes straight down from A to B. But then the other thing I want to do is I want to get dimensions starting at A, and our X and Y dimensions to that force at C, okay? Because I know I'm going to take moments about A, So what I want here is I want a set of dimensions that go from A to each of these forces. So I want that dimension, and that's quite easy. That's 3 centimeters. But then I want another set of dimensions, okay? And what I want is I want dimensions in the X and Y directions from A to C. So that's going to involve doing a little bit of trigonometry here on that angled arm, like so. Okay, and it's, you know, it's just right angle trig. Figure out that little vertex angle in there, and you got the hypotenuse of 8. So get those dimensions figured out, and then from those, get the x and y's from A to C. Now, if you remember, you know, I'm doing this on purpose. I'm getting the x and y dimensions because I'm going to use trig and break that reaction at C into x and y components, right? And so I'm doing this all on purpose. You know, I'm thinking ahead, and I'm getting everything set up so I can just do it. You know, I've got this reaction at C, and I know that that's a, 70-degree angle in there. And then I've got the reactions at A. And of course, I've got the 2 reactions at A. That's why I'm taking moments about A. And then I just want to solve for RC. So I want to get nice, clean dimensions from A to C. And I want x and y dimensions is what I want. So I'm going to do a little bit of trig there on that angled arm that goes from B to C. That way I can get those red dimensions directly from A to C. And this is the deal where it's kind of important in statics in any of these classes. Get beyond the picture, you know, whatever that is, a bracket, a wheelbarrow, a mechanism on a conveyor belt, an airplane, a dam, a building, a bridge, whatever the heck it is. I don't care what it is. I just want to connect the points together that have forces on them with dimensions, x and y dimensions. That's how I approach it. So you know, don't get hung up on the picture in front of your free body diagram. Just get those forces on there, figure out what we're going to take moments about, and connect that point to the forces with nice clean XY dimensions. That's all you got to do, okay? And it doesn't matter what the picture is. That's really irrelevant. It's just doing that. Okay. Okay, so just a little bit of right angle trig there should get you those 2 sides. 0.4 and 0.693, or 0.04 and 0.0693. I'm in meters. You could stay in centimeters if you wanted it. As long as you're consistent on your distance units on these, it really doesn't matter. But I'm just taking that armature from B to C and just doing a little bit of right angle trig. That's all I'm doing. Okay. But my longer range goal here is to come up with those dimensions from A to C. That's really what I want to do. So I want to get these dimensions. I'm kind of changing colors around here, but this is 0.693 now. And this other one is really pretty close, isn't it? It's 0.07. That's 0.0693, right? All right. So that's what I want. Everybody okay with what I'm saying there? Any questions on this stuff? So now what I've got everything connected together. See, and I've thought about this beforehand. I know I'm taking moments about A, and I've got dimensions from A to everything I need now. So now doing those moments is pretty straightforward now. Okay, so why don't you just do the moment about A there real quick. Get you a couple minutes on that. And remember, X moment arms with Y forces, Y moment arms with X forces. That's how you make moments. The force and the moment arm have to have different directions, X and Y. But using X and Y dimensions and X and Y components of force ensure that everything's at right angles for those moments. See? That's the idea. And then counterclockwise positive and clockwise negative. And that's about it. Should be getting to about 11.8. Something along those lines. Y'all doing okay with that? 3 terms, because the Y component of the 48 doesn't cause a moment. It goes right up that armature. So that's the deal. We got any questions on that? So it's important that you understand that, right? It's important that you understand that the first thing you do is you make a free body diagram. You reduce down any distributed loads into point loads. And then you decide where you're going to take moments about, and then you dimension from that point in the X and Y directions to all the forces.
Can you go back to the previous one with the triangles? I wrote down the wrong numbers.
I think they're right here, if 0.04 and 0.6. Oh, it's just sine and cosine.
Oh, I wrote down the wrong one. Right.
You good? So it's here, it's cosine 30 and sine 30,
Okay.
0.08. Everyone else is on this one. I just don't want to. We good on that? All right. So, and again, it doesn't matter what the picture is, what it is. You know, it's irrelevant. Just approach them that way, and you'll be able to do any of them, really. Okay. All right, then I got RC, okay? And now I've got RC. So, I just dimension that thing, so I don't have to think when I write that moment of equation. I just fill in the blanks, that's all I'm doing. I'm less likely to make errors. So now I got RC, so now the next thing I do is I use two simpler equations to solve for RAX and RAY. Sum of FX and sum of FY. Moment equations I'm more apt to make errors on, so I just do force equations for the last two. It's just easier, okay? We good on that? Any questions? So sum of FX, sum of FY, and then I'm done. Okay. Looks like in both cases I got positive answers for RAX and RAY, so they came out to the right and up. So RAX to the right minus cosine 43 times 48, that's to the left, plus cosine 70, 11.8 to the right. Get RAX is 31.1. And sum of FY, RAY up, minus sine 43, 48, which is down, because that 48 Newton force is down, and then plus sine 70, 11.8, the upward reaction there. Let's see. So we okay with that? It's basically the drill on this stuff. Okay. All right. All right, how about looking at this might have changed. I've got it marked 430 on my slide, but it might be old. 440, okay, 440, thanks. So why don't you give that a run, or let's just think about that. Let's get that thing turned into a free body diagram. Let's look on our speed here a little bit. Let's do that in 30 seconds. I think you can do it. I got faith in you. Okay. So 440, let's get that into a free body diagram. Remember to put the weight on that thing. The weight's 1.2 meters from point A on the bar. Okay. Something like that. I see a pin joint, I put the two reactions on that thing, I put the tension in at B, put a downward force in 1.2 meters from A. The weight goes straight down like weights do. Okay. We good? Okay. What's that now? Oh, yeah, that'd be the tension at B. I call it T. Sometimes you call tensions T. It's the reaction at B. The wire, the force in the wire. the vector sum of the two forces at A, the reactions at A. Okay. We good? We got that? Okay. All right, now let's do the standard approach on here. So what am I going to do? How am I going to start this thing out?
Make a table of,
What's that?
or no, at least the way I always do it is I make a table of X, Y, and X.
Okay. How about, let's figure out, what's the first equation I'm going to use? Why don't we start with that? Right, about where? A, okay? And that's a pin joint. So you can't lose if you do that, okay? Because you're going to eliminate two unknowns from the equation. You can pick up the third with the moment equation, okay? All right, now, if I'm going to take moments about A, I want to get X and Y dimensions to the forces that I'm going to work with from A. See, I want to get this identified so I know how to dimension the thing efficiently. So that's how I'm going to start this thing off. So what I want to do is I want to measure everything from A to the 240 and from A to what the tension at B or reaction at B, whatever you want to call it, okay? So I want those dimensions, X and Y dimensions, okay? So I want those green dimensions. I got X and Y dimensions there from A to B. I only got an X dimension from A to the 240 because 240 is vertical. All I need is an X dimension. There isn't a Y component to that 240, so I don't need an X, or excuse me, there's not an X component to the 240, so I don't need a Y dimension. So I need those three dimensions, okay? Now, you got the angle of the armature over there on the far right. It's 20 degrees. So just do a little bit of trig there and get those dimensions figured out. Just right angle trig, 20-degree armature.
Did you just rearrange the axis?
I'm not going to do that on this one yet. Just let's use straight axes on this, okay? Now you could incline axes. That might be another way to approach this. We might do it that way too, just for fun, but let's not on this one. What's that?
If we're so inclined.
If you're so inclined, yeah. Okay. Well, you got me to repeat that one. That was good. Okay, so so let's just do this straight up, X and Y, just for practice, because it's so much fun. Okay, so just a little bit of trig, okay? And we use lots of right angle trig in this class, sine and cosine. It's a 20-degree angle. $20. Okay. Okay, now when you're dealing with an angle with the horizontal, cosines X and sines Y, right? So cosine angle hypotenuse gets you the X, sine angle hypotenuse gets you the Y. That's if the angle is with the horizontal. What we got, we got a 20-degree angle with the horizontal. Y'all doing okay with those dimensions? Okay. Okay, now I got 1.13, I got 2.82, and I got 1.03. Are those okay? And see, I saw some of you doing moment equations, just get those dimensions first would be my suggestion. I compartmentalize my thinking. I just do the trig. I can do right angle trig. I don't think about anything else. I just think about right angle trig. I get that nice and dimensioned. After I've got those in there, then I'll do the moment equation. Because I'm not that bright, and if I try and do both at once, I screw things up. It's just how it works for me. So, okay, so I do the trig first. I just focus on the trig. Then I do the equation. Less errors, less people, less problems. So we good on those dimensions? Any questions on there? Right angle trig there? Okay. You okay with that? Once you got those in there, then you can do the moment equation because everything's good to go. See, you got all the stuff you need. Now, the one other thing you might need there is that angle of the cable at B. That's going to make a 42-degree angle with the horizontal up left because I've got a 48 up there with the vertical for that wire. 90 minus 48 is 42. And all I'm doing there is just using a right angle triangle, right triangle there. And
It's got a 62-degree angle.
that's true. It's also, is that what it was given? Was that 62 given?
Well,
Oh, if you're doing it the other way?
20 plus 42.
Yeah, although I'm just sticking straight XY here. I'm staying with that. So I got the 48 is given. So a full triangle is 180. So 90 for the right angle. I'll take away that, take away 48. And what that's equivalent to is just 90 minus 48, which is 42, either way. Okay. So that's where that comes from right there. Okay. So do a moment equation about A here for that, okay? Okay, so a moment equation about A. Can't remember what we're going to get out of that thing. 102, something like that. For the tension at B, 102. Okay, so X forces and Y moment arms, and Y forces and X moment arms. So that's how the moment equations work. Watch the directions. Clockwise positive, no, clockwise negative. Counterclockwise positive.
Just use the perpendicular component, the angle moments on it.
Yeah, and you can even mix those if you want, you know, I mean, it's not, you could like go,
That seems potentially dangerous.
yeah, but you know, sometimes we live for danger though, right? So 240 times 1.13, then you can take the sine 62 TB times the, whatever that is, the 3. You could do it that way too. It would work. Okay. So you should be getting 102 out of that moment arc, okay? Or out of the moment equation. Something like that. one negative moment and the other, and then the ones with TB are both positive about A. You okay with that moment equation? You have any questions? Get 102, then you go sum of fx and sum of fy and get the tension and, or excuse me, get the ax and ay reactions. Okay. All right, and if you want to find, everybody got that moment equation now? We good? And then sum of fx and sum of fy to finish the thing off. And then if you want, you can take the square root of some of the squares. If it's a real simple connection there, that'll get you the force on pin A. Okay. So there is kind of a standard drill on these things, you know, as I've said a few times now.
How much time would we have to do a problem like this on a test?
Oh. Well, that's a good question. Let me think. $10 to 15 minutes. And yeah, I think you're onto something there. I have been kind of relentlessly repeating myself about the importance of this, haven't I? So that might be a good question. But so the thing there is kind of like with that 3D stuff. I've told you the method 3 or 4 times. Get that figured out and write it down, you know. Go over it and then just apply it. You got time on test to apply things, but you don't have time there to scratch your head and go, oh, how should I do this? You know? So this, you know, this is a very distinct method, and get ready to apply it when you have to, right? Okay. And like I say, the picture that's used is irrelevant. It can be anything. It doesn't matter. It's just a force diagram when you do this stuff to it. That's all it is. Okay. So we okay on this? Sum of fx and sum of fy? All right. Okay, now, as a number of you have been pointing out, you could also use inclined axes on this if you wanted. And I think, do I have a second copy of this? Did I ever get around to doing that? I can't remember. I didn't, did I? Okay, you could, you know, put it down below or put it on the blank page that's facing this one or whatever, but you could do this one with inclined axes. Now, the one thing you would have to do on that approach is you'd have to figure out a couple of angles. Okay, now the first one is this one right here, 62. Now what we're doing there is, you know, there's different ways you could approach that, but you've got a 20 right here. So if that's 20, this angle up in here is 70, right? Because they make up a right angle right there. And if you've used 20, you got 70 left over. So now you got a 70 in that lower left-hand corner of this triangle. So you can do the math and take 180 minus 70 minus 48 and get 62. Okay? So if you're going to do these inclined axes, you're going to have to do a bit of geometry with angles. You know, that's just how that's going to be. So you can get that at 62, and then you can get this 240. See, that's going straight down. And then you've got a 20 up here. So you should be able to figure out this 70 here in one fashion or another. But that's straight down. That's 20 right there, right? So if that's 20, this is 20, and that'd be a 90, so this would be 70, which would be 90 minus 20, or 70. All right. So that gets me those angles that I need. So I get that free body diagram on an incline. See, this will work pretty well because I can get those angles pretty quickly. Plus, I've got the distances measured along the direction from A to B. I've got the 3 meter total, and then I've got I'm given that it's 1.2 meters from A to the center of gravity. Okay. So I can generate that free body diagram, and then I can just do the same process. I can take a moment about A, and see, this will go a little easier, you know, one less term. Instead of 3 terms, I'll only have 2. It's kind of like that one homework problem we did with that inclined bar that had forces on it, finding the moment, same thing. Okay. So then I can take moments, and I'll just have minus sine 70 times 240 times 1.2 plus sine 62 times the tension at B times 3. So, you know, a little bit easier to generate that moment equation. But the flip side of that is you've got to find the 62 and the 70-degree angles. So you got to do a little bit of geometry. Now, geometry is a good skill to have in the working world. I mean, you know, my experience, you know, I just worked as a regular engineer. I didn't do anything really fancy or anything. And, you know, some of the stuff you learn in school is a little bit more useful than other things, you know, when you start working, admittedly. And one thing that I found very useful was geometry, just a good, solid understanding of geometry, because, you know, I'm a civil engineer. You're always laying stuff out, spatially laying stuff out. Same thing with mechanicals. I mean, I did a pump station once, you know, I had a certain space to fit all the stuff in. Just had to be darn sure we weren't going to have any interference, you know, in that little pump house and that kind of thing. So, you know, or all the time I'm laying stuff out at angles and all that when I'm doing civil engineering, roads and pipes and all that. So I just have a good, solid understanding of geometry is a good skill, you know. So we want to get to that 70 and that 62. So, you know, again, just as I was doing up there when you're doing geometry, just draw sketches. That way you can't lie to yourself if you got good sketches. You know, then you're doing stuff that's, you know, good and theoretically correct, and it'll get you the right answers. You know? All right, so we do a moment about A now. A little bit easier moment equation there, but you get to the same answer, see? Doesn't, you know. And as I was saying, you know, if you could have, you know, if you could have just found this angle, and, you know, you can mix axes too. You could find that moment of B around A using the inclined axes, and then find the moment of the weight around A using straight up XY axes if you want. I mean, there's many different ways to approach this stuff. And you'd get the same answer. Okay, so 102, and then you can do the sum of fx prime and sum of fy prime. You'll get different components for x prime and y prime, of course, because you're using different axes. You're using inclined axes. But notice when you take the square root of sum of the square, you get the same force in the pin, because the force in the pin is what it is. Okay? So regardless of which set of x and y axes you use to get that, you know, you'll get the right answer. You know, they'll always come out to be 188. Okay. So we doing all right with that? Okay. Okay. All right, so that's another approach on that one. So, you know, sometimes these inclined axes can make problems easier. Now, sometimes you might have distributed load reactions that you might run into. You know, these will come up. I've done these before. I did a little dam once, and we made some assumptions on it that led to a distributed load reaction, basically. So what's going to happen with this dam here is you're going to get the force of the water pushing on the dam like that, and that's going to tend to take the whole dam and rotate it that way. So the soil is going to push back. So quite often an assumption you make is you got a pin joint on the dam, and the whole dam itself rotates like that, you know, as that, and I'm exaggerating, of course, how much it would rotate, but that's, you know, that's the assumption. So when the soil pushes back, what you get is a distributed load that increases the further you get from the front edge of that dam, because you get more rotation pushing down on the soil. So you end up with a trapezoidal kind of load pushing back, okay? That's a common assumption you make. Yeah, it's one of those things that aren't perfect, you know, but, you know, like I say, just throw a safety factor in there and go with it and get some numbers and off you go, you know. I mean, I don't mean to be that flippant about it, but, you know, there isn't a perfect model, especially in civil. I mean, it's, like I say, it's dirt and pavement and stuff like that. It doesn't lend itself to perfect modeling. Okay. So let's see, what do we got? We got 147, okay. So we'll look at an example of that tomorrow, I guess. Why don't I give you some of these to work on the weekend, though? And these might, you know, these could be a little challenging, you know, some of these, so maybe give yourself some time. So I'll get you a few of these. So 271. Now, just use standard XY axes for that one. It's really not worthwhile to try and incline axes on that. You can do it, but it's kind of more trouble than it's worth, I think. So just use standard XY axes on that one. 272 is kind of a good one there. We'll get you a couple others. About 274, that's one for inclined axes. What you got there is a car on a ramp. And if you want, that might require you to be a little creative. So 276, let's try that. And these will be due Wednesday. The 8th. Okay.
Yeah, it did. All right.